Hey guys, and welcome back to the Dynamics video series. This is going to be the newest video on the rotation moments of bodies that aren't rotating. So this is the first topic we're going to talk about after the third exam. I hope it went well for you. And essentially what this is adding from what you already know is all the stuff we've been doing, but we're going to be adding forces and free body diagrams and equations and such. This is a little bit of a simpler problem. It's on the homework, but I see it was causing some trouble, so we can actually go over it here. So a very important thing about this problem, we'll get into it, right? A 20 kilogram cabinet is mounted on casters that are locked and sliding on the rough, I'm pretty sure that should say floor, not door, with a kinetic friction of 0.25. If a 100 Newton force is applied as shown, and the distance is h equals 0.5 from that 100 Newton force to the ground, we have to determine the acceleration of the cabinet, right? And we're going to be assuming that the cabinet does not tip over. So how do we start here, right? So I would start by labeling my forces. So I'm gonna need some type of free body diagram. I'm gonna start drawing forces because I'm looking for an acceleration, but there's an acceleration not given. This thing is gonna be having 1 degree of freedom because if you can imagine, we know this thing is not tipping, so it's just gonna be going back and forth. And if I stop that horizontal translation, then there is no more movement, right? So we have 1 degree of freedom with what's it called? No accelerations given. We're looking for acceleration, so we're gonna have to label some forces here. So let's start doing that. So the first one I see is this gravitational force, right? The action at a distance, which has a magnitude of mg, right? Pointing straight down towards the center of the Earth. I'll just redraw this arrow. So this is my 100 Newton arrow. And I have some other contact forces, right? So I have a contact with this wheel or this, what they call it? This caster on the ground. And then this caster on the ground. Now we can't treat these as equal because this thing is being loaded from the side, right? Which is going to cause an unequal distribution of the weight. So we're going to label them differently. Let's just say this one is N1, and then this one over here is N2, right? Represent the first and the second caster. Okay, so we have all our forces. Could we just start summing forces in the X and forces in the Y? Now you're tempted to do that. And if you didn't know that this was a moment, maybe that's how you would start. But you'd quickly realize that we have 2 unknown forces in the Y, right? And with the Y, we can only get 1 equation there, right? So we wouldn't be able to solve for either of those. Now, if we can't solve for either of those, then we won't be able to use that in the X to get their frictions, right? Because these wheels also have friction that was known based on the friction coefficient, right? So these frictions are going to be that what's called friction constant, so mu k, times this one would be N1, and then mu k, and this one would be N2. Okay. If we don't know either of those, then we can't solve for the forces in the X to get the acceleration, and then nothing works out. So what the first thing we have to do is analyze it with a moment equation. Now, what moment equation can we use? Right. So let's imagine if this thing was about to start tipping over. Right. So if it was to start tipping over, what would happen? Right. Which point would it tip over about? If it was going to tip over, it would tip over probably, if you can imagine it, about this front wheel. Right. So if it tips over about that front wheel is now locked in place, right? And we can treat it like that. So we have a couple things going on at the moment it's about to start tipping over. We have this force, right? The normal creating a moment about that point. We have the applied force, the 100 newtons, creating a moment. And we have the gravitational force creating a moment about that point, right? And the sum of those moments is going to determine how fast this thing would rotate, right? If it started tipping over. What forces we would not expect to create a moment would be N2 because it passes directly through the point, right? So there's a moment is a force at over a distance, and so this force over a distance, there's no distance here because it's going straight through the point. So N2 would not create a moment. Same thing with this one and this too, because their line of action falls through that point, right? So we would expect none of those 3 to create a moment about this point. Let's label it something like point A just to keep it consistent. And so for the first thing I'm going to do is actually go sum the moments about point A, right? So I mean, point A is going to be fixed when if this thing were to start rotating, right? And that's going to help us solve for variables. So let's assume, I don't know, counterclockwise is positive. You can pick whichever you like more. This is what I'll do. So if I assume counterclockwise is positive, now I'm going to start by summing, let's say, that 100 Newton force, right? So the 100 Newton force is going to be trying to rotate this cabinet this way, or clockwise about the point. So this is going to be minus 100, and then times the distance that it is. So this is going to be this vertical distance, right? we said was 0.5 meters, 0.5, based on the problem given, right? So it's going to be 0.5 here. Okay, what else do we have? We have the mg. So the mg is going to be trying to rotate this thing in the opposite direction, right? It's going to be trying to rotate it into the ground. So it's going to be a positive moment from mg. So there's going to be plus mg times, and then the distance from mg perpendicularly to this point. This distance is half of the width, so this is going to be 0.3 meters. So times 0.3. Okay. And now we also have one more, and we said this N1 is going to cause some rotation. The reason we can treat N1 as something that's going to cause a moment is because we're assuming that this is about to start rotating about this point A. So we're assuming point A is a fixed point, but not that it is already rotating about point A. If it was already rotating about point A, then N1, you can imagine this door would be off the ground, right, or this cabinet. And if the cabinet is off the ground, then there's no contact between that caster and the floor, so N1 becomes 0, right? And then from there, if N1 is 0, we can calculate the acceleration based on the moment of inertia with these other forces we have, but we're assuming it's still in contact with the floor, just about to start rotating. Okay, so now I'm going to do N1. So this is minus N1 because it wants to rotate it clockwise. And then N1 is the whole width apart, so that's 0.6 meters. And that's going to equal to 0, right? The reason it equals 0 is we're assuming that it's gonna not moving yet. It's kind of still in a state of equilibrium because this cabinet was said to not tip over, right? So we're gonna treat it as such. So when we do this, we're gonna want to firstly solve for N1, right? Because that's our only unknown variable here. So let's do that first. So N1 is, so let's see what these values are. So this 100 is going to be negative 50, right, from this term. The gravity is going to be, let's see, 20 is the weight times 9.8 times 0.3. That's going to be 58.8. And that's going to be minus 0.6 and 1 equals 0. All right. So now we can move this 0.6 and 1 over, right, just to solve our algebra. And we're going to get that 8.8 equals 0.6 and 1. And we're going to get from that, that N1 is equal to 8.8 divided by 0.6, which is 14.66. And that's going to be in the upwards direction. That makes sense because right now it's pressing, the floor is pressing into that caster. Okay, now we can use that and sum our forces in our y to solve for our N2 value, since we only have gravity N1 and N2 in our y direction. So I'm going to do that here. So sum of my forces in my y is going to be plus N1 plus N2 minus mg, all equal to 0, because this thing is not tipping, it's not accelerating in a y direction, only in the x, which is left and right. We're treating y's up and down. So we can actually just plug in and solve. So N1 was 14.66, N2 is what we're looking for, and then minus our 20 times 9.8, and that's going to be equal to 0. So we'll move that 20 over, or 20 times 9.8 over. So 20 times 9.8 is 196 minus 14.66 is going to be equal to, 196 minus 14.66, 181.33. Okay, cool. So now we have our N1 and our N2. And now we can do our last step, which is sum the forces in the x direction and get our acceleration. So let's do that. I'm going to create these little dots just to separate it. So let's do that in this last little section. So I'm going to sum my forces here in the x. All right. And when I do this, I'm going to assume right as positive. So I'm going to have a plus 100 in the x minus, and then I'm going to have the mu k N1 and the mu k N2. So mu k is, well, I'll just write it out first. So mu k N1 minus mu k N2. And that's going to be equal to our mass, right, times our acceleration in the x, and that's going to be our answer, right, because that's the only way that this cabinet is accelerating. So this is going to be 100 minus, and then this is now mu k is 0.25. And that's times our 14.66 and 1. And then minus, I'm running out of room here. Let me slide this over, actually. Not that much. There you go. And then that's minus, again, 0.25, coefficient of kinetic friction. And then our 181.3 and 2. And that's going to be equal to our mass, which was 20, times our acceleration in the x. Right? And then when I do the sum of the terms on the left side, I get 100 minus 0.25 of 14.66 minus 0.25 of 181.33. And that's going to be almost exactly 51. Right? And that's going to be equal to 20 times our acceleration in the x. And then we'll just divide both sides by 20 and get that our acceleration in the x is going to be equal to, so this divided by 20, about 2.55. This will be meters per second squared in the right direction, right? So this cabinet is accelerating to the right when we push it to the right, so that makes sense. So that's going to be our final answer for this problem. I hope that makes sense. So the first thing we have to do here is different from what we did at the beginning of the semester. We have to sum moments. So it's important to remember how to sum moments and which forces are going to create moments about certain points. That's kind of the essence here. It was helpful that it told us that the cabinet did not tip over. If it didn't tell us that, then we have to first assume that it might, right? So we would have to create like our table and stuff like that. But in this case, we didn't have to since we told it was not tipping over. Okay. Well, that's going to be the end of this problem. See you.